We have defined orthogonality between two vectors. Now let's define an orthogonal set. When it comes to bases, very often we would like to use orthonormal bases. Now, if we are given a basis that is not orthogonal, a non-orthogonal basis, is it possible to convert it to an orthogonal basis? And that's the topic that we are going to talk about here. For example, suppose S equal to the set of U1 and U2. It is a basis for R2. This is U1 and this is U2. And we would like to convert it to an orthogonal basis. For example, we can choose V1, we can choose U1, and then we can choose another vector in here to make it orthogonal. How can we do that? For example, we can do this one, do the orthogonal projection of U2 on the line of U1. And let's say this vector is W. And this is U2. Then this one would be U2 minus W. This vector is U2 minus W, and so we would have U2 minus W here. This is U2 minus W, and if we throw in U2 minus W here, will this be an orthogonal basis? Yes, that will be an orthogonal basis. So now we have convert a basis, now orthogonal basis, to an orthogonal basis for R2. This S prime is such a basis. That's the two-dimensional case. Now let's try to consider a more general n-dimensional case. Let's formally introduce orthogonal projection. Orthogonal projection of a vector on a line. We will be using orthogonal projection very often. We will use the abbreviation OP. The orthogonal projection of a vector on a line. Suppose we have a U2 vector in Rn, and L is the line formed by this U1 vector. So let's say we have this U1 vector, and we have U2 vector. Let me draw it a little bit nicer. U1 vector here, and from this U1 vector we have this line L, and we have U2 vector here. W is the vector on L, such that U2 minus W is perpendicular to U1. And this W is called the orthogonal projection of U2 on L. So what is W? W is such that it's a vector on L, and W is a special. Why? Because not just an arbitrary vector on L, it's a vector on L such that this U2 minus W and the U1 are orthogonal. So this is U2 minus W. This U2 minus W and U1 are orthogonal. In this case, we say W is the orthogonal projection of U2 on the line L. I have drawn this line in like a two-dimensional case, so that's easy to understand. The definition of orthogonal projection is given like this. It's the vector on L such that these two vectors are orthogonal. And it doesn't give us a specific way of computing W, but it's possible to do that. So let's see how we can determine the orthogonal projection W. Suppose W is equal to CU1 because it's a vector on L, so it can be expressed as CU1. So if we plug in this W expression, that's C is the scalar that we want to find. If we can find C, then we can determine orthogonal projection vector W exactly. Let's plug in this expression into here. U1 transpose and U2 minus W are orthogonal. So U1 transpose and U2 minus CU1 is 0. And this means that the dot product of U1 and U2 on the left hand side, and we can move this term to the other side. We get C times U1 transpose U1. Wow, we have C. We can get C by moving this term to the left hand side here, and we get C coefficient. Now we can determine the orthogonal projection exactly. The W vector is a scalar, and U1 scaled by this scalar, and this is a scalar is the dot product of U1 and U2 divided by the norm square of U1. A question: suppose S is a basis for a subspace V of Rn. Now S prime is equal to U1 and then U2 minus W. W is the orthogonal projection of U2 on the line of U2 on the line of U1, like what we have here. And with this S prime an orthogonal basis for V. For S prime to be a basis, it has to be linearly independent. It has to be a generating set and it has to be orthogonal. So we ask if S prime is orthogonal, and that's indeed the case. And is it a basis for V? And it's a linearly independent set, right? It follows directly from the orthogonality of S prime. And to show S prime is a basis, it's linearly independent and it's a basis, there are a couple of ways to do it. For example, in this case, the number of vectors in S prime the same as the dimension of V. It's linearly independent, and the number of vectors in S prime same as dimension V, so S prime is a basis. So yes. So this S prime, if we have a V1, V2 vector, where V1 is equal to U1, and this V2 is equal to U2, minus the orthogonal projection of U2 along the line of V1, then S prime is an orthogonal basis for V. How about the case when S has 3 vectors? S is a basis for a subspace W of Rn. How to obtain an orthogonal basis for W? Don't worry, we are not going to ask for the case that S has 4 vectors. We will stop at 3. So let's work on the case. If we have 3 vectors, and we would like to convert it to an orthogonal basis. For 2 vector case, we already know how to do it. So we can choose the first one, vector U1 as the first vector. And then for the second vector, we subtract from U1 the orthogonal projection of U2, or subtract from U2 the orthogonal projection of U2 on the line of V1. Then we know this V1, V2, this U1, U2 can be replaced by V1, V2, and U3 is still here, this continues to be a basis for W. But our job is not finished yet, right? Because V1 and V2 are orthogonal, but U3 is not orthogonal to U3 is not orthogonal to V1 and V2 yet. So we need to do something about this. We want to choose the last vector so that it's orthogonal to V1 and V2. So, following the steps that we have done before, we know if we subtract the orthogonal projection of U3 and the line of V1 from U3, then we will make this vector. We can make the whole vector orthogonal to V1. In addition, we also subtract from U3 the orthogonal projection of U3 on the line of V2. That will make U3, that will make the vector orthogonal to V2. Now let's see if the V3 that we have so defined is orthogonal to V1. So let's multiply V1 transpose on both sides. Then on the right hand side we can use in the bracket we have U3 from here, and we have this term from here. How about the last one? The last one is gone. Why? Because V1 is orthogonal to V2 already, so we don't need to keep this term anymore. And then this term is actually U3 with the orthogonal projection of U3 on the line of V1 subtracted, so it's orthogonal to V1. And we can verify that it's indeed 0, like what we had done before. Similarly, if we multiply both sides by V2 transpose, so V2 transpose V3, and then V2 transpose, this time we are skipping this term because we already know V1 and V2 are orthogonal. So we are left with the first term and the last term in the parenthesis. And it's again 0. So now the V1, V2, V3 vectors that we have found are indeed orthogonal, and they are linearly independent. Now S and S prime have the same number of vectors, and they are both linearly independent. And so now if span S prime is contained in span S, if this is true, then we are done. Then we can show that S prime is indeed a basis for span S. Is this true? That's true. Why? Because all these V1, V2, and V3 vectors, they are linear combination of U. V1 is equal to U1, V2 is U, and V1 is again U1, and V1 linear combination U3 and V1 is U1, and V2 is a linear combination of U1 and U2. So indeed, span S prime is contained in span S, so we can conclude S prime is a basis for W. Now we are ready to generalize what we have been talking about to a more general case, the Gram-Schmidt process that converts an arbitrary basis, U1 to UK is a basis for a subspace W for Rn. The process converts the basis to an orthogonal basis V1 to VK for W. As we have done before, V1 is chosen the same as U1. V2 is U2 minus the orthogonal projection of U2 on V1. V3 is the orthogonal is U3 minus the orthogonal projection of U3 on V1 and the orthogonal projection of U3 on V2, and all the way to VI, it's UI minus the orthogonal projection of UI on V1 all the way to the orthogonal projection of UI on VI minus 1 for I goes from 1 to k. Then these V vectors will form an orthogonal basis for W. Here's the proof. We let Si to be the vector of U1 to Ui, it has an I vector, and Si prime to be the set of V1 to Vi, also I vector. And the claim we have here is Si prime is orthogonal and span Si prime is the same as span Si. If we can show this, then the proof is done. If we are able to show this is true, then we have in fact shown the theorem. And we're going to show it by induction. Suppose Si minus 1 prime is orthogonal and span Si minus 1 prime is equal to span Si minus 1. And suppose this is true, and we are going to show that then Si prime is orthogonal and it has the same span as Si. So we already know Si minus 1 prime is orthogonal. And now we want to show Si prime is orthogonal. Si prime has only one additional vector, which is the Vi, and this is how Vi is defined. To show that Si prime is orthogonal, we only need to show that this Vi is orthogonal to all the other vectors V1 to Vi minus 1. Why? Because we already know V1 to Vi minus 1 are orthogonal, because Si minus 1 prime is orthogonal. So we form the dot product Vi transpose Vi, and then this is what we get. And although there are so many terms, but only one term will stay, which is the term of V1. And this becomes, all the other terms will go away, only this term will stay. And this is the orthogonal projection of the Ui on V1, and we subtract this orthogonal projection from Ui, so it will be orthogonal to V1. So this is 0. In exactly the same way, we can show that Vj transpose Vi is 0 for j from 1 to I minus 1. So Si prime is indeed orthogonal. Now there's one more thing to show. We want to show span Si prime and Si have the same span. Vi is a linear combination of V1 to Vi minus 1 and then Ui. It has Ui, it has V1, it has all the way to Vi minus 1. So it's a linear combination of these vectors. But then each V is a linear combination of the U vector. So Vi is actually a linear combination of U1 to Ui vectors. So the span of Si prime will be contained in the span of Si. And we know they have the same dimension because the two sets have the same number of vectors. So there we go. Span Si prime is indeed equal to span Si. A question. Just now we saw that Vi is a linear combination of U1 to Ui. U1 to Ui. Can we say it the other way around? Is Ui a linear combination of V1 to Vi? Indeed we can. Why? Because Vi is equal to Ui and all these Vi terms. Now if we move all these v1 to vi minus 1 to the other side, then we get ui equal to vi, and then uv1 all the way to vi minus 1. So ui is a linear combination of all these v vectors. Question. We know S prime is an orthogonal basis. We already convert from S to S prime and we have an orthogonal basis. But what if we want an orthonormal basis? Can we get it from S prime? That would be possible, right? And that should not be too difficult. We can simply normalize every vector in S prime. V1 normalized by the norm of V1, and then V2 normalized by the norm of V2. We do this for every vector, then we get an orthonormal basis for W. A byproduct that we can get from Gram-Schmidt process is QR factorization. And this is also an alternative to Gaussian elimination for solving systems of linear equations. Let's use one example to explain what QR factorization is. Suppose A is a 3x3 matrix, has a 3 column vectors, u1, u2, u3, and these vectors are linearly independent. Then we can apply Gram-Schmidt to these vectors and obtain an orthogonal set v1, v2, and v3. According to theorem 6.6, vi vector is ui subtract and minus the orthogonal projection ui on v1 and all the way to the orthogonal projection of ui on vi minus 1. Now let's move all these orthogonal projection terms to the left-hand side. Then on the right-hand side, we get ui. And on the left-hand side, now we have moved all those vectors here. They would be these orthogonal projection terms plus vi. And we immediately see this is actually a linear combination. ui is a linear combination of u1 to ui. It depends only on u1, v1 to vi, but does not the vectors after vi plus 1, vi plus 2. It does not depend on these vectors. In particular, u1 is the same as v1, u2 is a linear combination of v1 and v2, and u3 is a linear combination of v1, v3, v1, v2, and v3. Now let's normalize all these vi vectors and call them vi prime. We put these vi prime vectors into one matrix, vi prime, v2 prime, and v3 prime, and call this Q. Then the first vector, u1, would be Q and a column vector of this form, because it only depends on the first column vector of Q. u1 only depends on the first column vector of Q. So when we write u1 as a linear combination of v1 prime, v2 prime, and v3 prime, only the first element is non-zero and the other two are zeros. And what is the first element? The first element would simply be the norm of v1. Similarly, u2, when we write it as a matrix vector product like this, only the first two elements are non-zero and the last one is 0, and R22 is the norm of v2. u3, a linear combination of all three vectors, so we put down r13, r23, r33 for some scalars, r scalars, and r33 is the norm of v3. Now putting all these together, we have A equal to Q and R1100, R12, R220 here, and R13, R23, R33 vector here. So now what we have here is a factorization of A. We have factorized A into two matrices. One is a matrix that has orthonormal column, and the other one is an upper triangular matrix. In this construction of a QR factorization, the R diagonal entries of R are equal to the norm of VI, and so they are all positive. Now let's state formally the QR factorization result. That A is an n by n matrix, and the column vectors are linearly independent. Then there exists an n by n matrix Q, the same size as A, whose columns form an orthonormal set in Rn, and also a square n by n upper triangular matrix R, so that A is equal to the product QR. And furthermore, R can be chosen to have positive diagonal entries. We mentioned earlier that we can use QR factorization to solve a system of linear equations. Now let's do that. Let's consider the system of linear equation AX equal to B, and so we have a QRX equal to B, where we have used a QR factorization of A. Let's multiply both sides by Q transpose. So we have Q transpose on this side and Q transpose on this side. You will be asked to show that this Q transpose Q is actually equal to an identity matrix. Let's call the vector on the right hand side B prime. Then we can simplify the equation as Rx equal to B prime. Let's use one example to illustrate how this equation can be used to solve system of linear equation now. So now we have Rx equal to B prime. If A is a 3 by 3, then this R is a 3 by 3 like what we had earlier. And we have x1, x2, x3, and on the right hand side b1 prime, b2 prime, and b3 prime. If we write down the individual equations, then this is what we have. For the first one, we have r11, x1, r12, x2, r13, x3 equal to b1 prime. And for the second equation, we get r22, x2 plus r23, x3 equal to b2 prime. And the last one, r33, x3 equal to b3 prime. Now, is there an easy way to solve this? Well, we see x3 is already obvious, right? So we can solve x3 using the third equation. And after we solve x3, this is known. x3 is already known, then we can move it to the right hand side. Now there's only one variable to be solved. That would be x2. So x2 can be solved using the second equation and the knowledge of x3. Now we are down to the last variable. For the first equation, we see that we have x2 and x3, which we have already known. So these two terms are already known, and they can be moved to the right hand side, and we can use this to solve x1. So there we go. x1 can be solved using x to the first equation and the knowledge of x3 and x2. So because of this structure, this upper triangular structure, we can always stop at the bottom equation and solve the lost variable. And then we move one equation up to solve the next variable. And then we move one equation up to solve the next variable. And so on and so forth.